What's going on? There's my note. There's my note. Okay, so I guess the first thing, from 9 and 10, science, let's see if we can remember what we mean by matter. What's that term mean? Yeah? Okay, very good. So, has mass. Okay, what else? That's half of sort of the classic definition of matter. In the classical definition of matter, we say that matter is anything that has mass and... What's that? Occupies space. Still batting 1,000. Still batting 1,000. Look at that. So has mass and occupies space. Absolutely. So that would mean that, the air in the room has mass. You can weigh it. Hard to weigh with like a natural scale, but it has mass and it occupies space. But you, the desk, the table, all those things. What about light? Does light matter? Does light have mass? No. So we would qualify that as something differently. Electrical energy isn't matter, right? It doesn't have mass. Light can occupy space, right? There's light filling this room right now, but has no mass, so we wouldn't say that it's matter. What else do we typically say about matter? Does anyone know? Any other things we could typically say? Yeah. Yeah, absolutely. Yeah, I like that. Okay. Yeah, and those two kind of fit together, right? Like the way we classify matter is by what its atoms are, like what it's actually made of. So it is made up of particles called atoms. Okay. And we'll learn more about the atom tomorrow. But enough to say for the moment, atoms are sort of what we think of as the smallest particles of matter. Now, the truth is, if you get going in chemistry, we learn about smaller particles. The atom itself, you know what they're made of, right? Does anyone remember the subatomic particles, the particles that make up the atom? Neutrons, protons, and electrons. Good. And then scientists have delved down, and we understand that there's particles that make up those themselves. These are what we call sort of the muons, the quarks, and you may have heard of some of these things. You don't have to worry about that today. But the point being, we think of the atom as the basic building block of matter. And this is why I always say chemistry is just Lego. If you can play with Lego, you can do chemistry. And like that's not even an exaggeration, it's just the same thing. It's the idea of putting blocks together in different ways to do different things. That's what you do with Lego, that's what you do with chemistry. Lego's a little bit easier because they're big and you can see them and they snap together. Chemistry is a little harder because they're really small and you can't see them, but they still snap together and you're just putting blocks together. Does that make sense? So the first classification we normally do is we put into two groups. We will say things can be either pure substances or things can be mixtures, right? I'm glad I left this huge space only to then have the title pure substances right here, but that's okay. It's the kind of efficient use of space that you will come to know me for. What's pure substance? Am I a pure substance? Wow, that was a quick answer. I feel so impure. Yeah. Okay. Okay, so oxygen's pure substance. And yeah, it's on the periodic table. Is water on the periodic table? Is water a pure substance? Ooh, I like this. We have disagreement. In this class, we handle disagreements one way and one way only. Arm wrestles. Now, if you want to arm wrestle to the death, that's your business. I don't really know what that would look like, but I'm curious to find out. Science, right? Why do you say it is a pure substance? This is the right answer. I like it. Why is water a pure substance even though it's not all made of the same atoms? Because we know what water is made of, right? What's the formula for water? H2O, which means what? Two hydrogens that are stuck to one oxygen. Does that make sense? So we still consider it a pure substance because they're stuck together. Does that make sense? Like truly stuck together. they've been, in Lego terms, like you've clipped them together. It's not a red block over here and a blue block over there and another blue block over there. It's the three of them clipped together, and now they're making a single piece. Does that make sense? As long as they're stuck together, that's a single particle. That's a single thing, even if it's made of a few blocks. We call that a compound, and a compound is still a pure substance. So a pure substance is any material, any substance composed of only one type of particle. Now that doesn't mean one type of atom, one type of particle. What's a particle? Well, that particle could be a single element, in which case it's all the same atom. So an example of that would be aluminum, right? If you got an aluminum rod, if it was like perfectly pure, every single atom in that would be aluminum. Does that make sense? If you got an iron nail, if it was perfectly pure, every single atom would just be iron. Oxygen gas, if it's perfectly pure, every single atom would just be oxygen. So it could be an element, but it could also be a compound, which is several atoms stuck together. And there's a term we tend to use in chemistry that means stuck together. Very good. Bonded or bound, both are acceptable. I'm actually going to say bonded. And an example there would be water, where every single particle is two hydrogens stuck to an oxygen, which literally kind of looks like an oxygen in the middle. And we usually draw it with hydrogen molecule or atoms attached to it looking like that. Excuse me. Can you think of another example of a compound? Yeah. Sodium chloride, right? Which is table salt. That is one sodium stuck to one chlorine. You could have carbon dioxide. What's that formula? Yeah, very good. That's a carbon stuck to two oxygens. So if you have a sample of carbon dioxide, if you look at it, every single little particle is one carbon stuck to two oxygens. So even though there's a mixture of different atoms, it's not a random mixture. They're not floating around randomly. They are stuck together and bounded. That is a single that's a single particle. That's a single type of matter. And so if that's all you have, we would still call that a pure substance. Does that feel a little bit familiar from grade 9? Good. It's important that you be comfortable with these terms, element and compound, because they're going to come up a lot. And you'll see some synonyms for compound. What's a synonym? Words that mean similar, the same thing. You'll see the term molecule. That's the main one. That's sort of the most common one you're going to see. But you might see structure. You can talk about, you might hear the term species. Sometimes we talk about chemical species. That's more when we get into sort of advanced organic chemistry. Like if you take the grade 12 chemistry, you'll see that term come up. But just to be aware of them, that you might see those terms from time to time. Can everyone see my writing okay? My projector has been getting progressively dimmer. I need to look into getting a new bulb. I'm feeling a little bit guilty about that. I will try to ameliorate that as quickly as I can. Any questions about that? Now, what happens if you take two pure substances and you put them together? Could I take the pure substance water and put it together with the pure substance sodium chloride? What would I get? Okay. What would we call it? Sure, and what would we call that? It has a name. Salt water, right? Right? You go to the ocean, there's salt water, right? That's not a very creative name, is it? But at the same time, like, that is. What if I took my pure substance, and is it like water? Well, kind of. It's a liquid and it moves, but sure tastes different, right? And like you can't drink it to survive. It'll kill you. It'll actually dehydrate you despite you drinking it. What if I took water and mixed it with carbon dioxide? Does anyone know what we get then? We get a new thing. We get a mixture. Yeah, that's right, soda water. If you dissolve carbon dioxide in water, it dissolves. It forms something called carbonic acid, which is why sparkling water has that kind of sharp taste to it. But then it makes its way back out. It bubbles out. And so it not only does it get that kind of sharp acidic taste, but it also is bubbly, right? Because you force more carbon dioxide into it than it can end up handling. So we can put things together. And when we put things together, we get mixtures. And with a mixture, there's two ways you can do that. There's two types of mixtures, two ways you can put things together. We can get what's called a solution, or we can get what's called sometimes a mechanical mixture, a term I hate, or what we call a suspension. And as a chemist, more often we'll call it a suspension. What's the difference there? Yeah. Yeah. So in a solution, these are evenly mixed at the atomic level. And that means there's only one visible phase, which is just a fancy way of saying it all looks the same. Does that make sense? So with salt water, there are two different compounds in there. There's sodium chloride floating around, and there's water floating around, but they are mixed at the individual atom level. You have a water molecule here, and a sodium ion here, and a chloride ion there, and they are floating around each other. So at our scale, you can't possibly see the individual pieces because they're mixed right together, right down at the atom. Does that make sense? Versus in a mechanical mixture or a suspension, this is mixed at a much bigger scale. Which means you can more than one visible phase, which is just a fancy way of saying you can see the parts. What's an example of that? Yeah, sand, what's that? Nice and loudly, I'm old and deaf. Oil and water, right? Yeah, a chocolate chip cookie, concrete, right? You can see the little aggregate bits. Most things that get mixed together, you kind of think of in this way, right? Like you can see the bits, salad dressing, right? Like you can see all the little bits floating in it. So you can see the parts. So take a minute and classify those there. Are we going to get? Yeah, we'll get there. Yeah. Oh, yeah. So what I want you to do, of course, yeah.
If you have a question about this, don't even ask me. Go ask somebody else.
All right, what do we got? Pure water. Pure substance or a mixture? Pure substance, specifically element or compound? Compound, good. Aluminum. Oh, man, I've already used these two examples. Sorry? Sorry, I'm not saying you're wrong or right, I just actually can't hear you. You answered, yes?
Is it AL?
It is, yeah. So is that pure substance or a mixture? It's pure substance. And is that compound or an element? Yeah, it's an element. It's on the periodic table. It's one of our types of atoms. What about gasoline? You might not know this. Where's gasoline come from? What? No. That's a terrible answer. Be more like Angela. God. Angela batting 1,000. What kind of an answer was that? Yeah. Sorry? Yeah, it literally comes from like fossilized animals, but mostly plants found underground and dug up. And then we like divide it into parts, and the stuff that weighs within a certain range we call gasoline, and we throw it in our tanks. But it's a mixture of like millions of different chemicals. Right? It's just a massive big slop. So it's a mixture for sure. Now, having said that, can you see the individual parts? In gasoline, can you see different chemicals floating around? No, it just looks like a liquid, right? So would that be a solution or a mechanical mixture? That's a solution. What about air? Yeah, it's another mixture. It's a solution. At least it should be. If you can see the individual parts of your air, that solves the problem. What about tap water? Mixture. What type? Yeah, hopefully. Again, if you're opening the tap and you see individual things floating around, might be time to like change your faucet, your pipes. I don't know. Steel. Is steel on the periodic table? Do you know what steel is? It's called an alloy. It's interesting. How do you make steel? Does anyone know? And has nobody ever gone down the rabbit hole of like watching videos on YouTube of like how they like these people who forge and like make swords like by hand? You have. Yeah, you have. You mentioned Shawn Michaels earlier. So like after I was done watching my WWE videos, I was like, I gotta watch a guy make swords with a hammer. But yeah, you take iron and you mix it with ash, which is just what on the periodic table? Anyone know? Yeah, what's ash? Ash is just you burn a tree, you burn plants, you burn your loved ones after they pass away. You're left with ash, which is primarily what? Carbon. Very good. I've always said I want to just be stuffed and put in the back of my classroom, but maybe I should be cremated and have them turn me into steel. Wouldn't it be great to have a sword that's made from like my mortal remains? I'm just thinking about this now. I think I like that. Well, why not, right? I could be a sword. I would way rather be a sword than be jewelry. Way rather. Okay, we're onto a thing here. Find that?
There's one that has no.
You found them on. Good. Yep. Yeah, you're good. All right. So now, having said that, when you look at a piece of steel, can you see little bits of carbon and little bits of metal? Nah, it looks all the same throughout. So it's a mixture. Specifically, it's a solution, and it's actually a specific example of that when we have a solution of metals. Does anyone know what we call it? I think I already said the word. I heard it. Yeah, it is an alloy. With an exclamation mark, it looks like it's ahoy. It's like you should be greeting somebody. Salad dressing. Mixture, and in this case we can see the parts, so we'd call that a mechanical mixture. What about smog? Does anyone know what smog is? Smog is less of a problem now than when I was a kid. When I was a kid, environmental regulations were more lax, and like you'd drive by Hamilton, but even like you'd get like air from Hamilton like blowing into the Niagara region, and like it would be like smog, which is like this like thick, dense, like smoky, foggy, gross, which is what it is. Smog is a portmanteau of the word smoke and fog. Isn't that gross? But famously, like in the Industrial Revolution, when they first started like factories and burning coal in London, London would spend just whole months just completely enveloped in smog, where just you couldn't see like 2 feet in front of you, and it was a mixture of fog, which London is already bad for, and just like thick smoke from like the factories, which sounds pretty gross and was terrible for people's health, as you can imagine. Pure substance, mixture, solution or mechanical? I'm going to say mechanical. In this case, we know that air, which is part of smog, is clear, but then we're also seeing dark bits in it. And have you experienced this before, where even with just your visible eye, on a foggy day, you can actually see almost individual little droplets, right? You've ever experienced that? Have you not? Oh, get a magnifying glass, team. Or reading glasses if you like. All right, so we're going to really quickly review kind of the history of the atom and how we get to this place. Because we have this kind of classification here, and it's all based on atoms. So, what's an atom? I already told you that when I was in elementary school, you could bank on there being 2 or 5 of them into your class. But that was atom with a DA. This is atom with a TO. So, what's an atom? Don't judge me. In my class, we had Adam MacArthur, we had Adam Netherway, and we had Adam, what's his last name? What was his name? Oh, obviously not a very memorable guy. Not like that Adam MacArthur. That guy was memorable. Anyway, that guy was smart. He used to make me mad. He beat me on everything. Always got better grades than I did. Made me very angry. So what's an atom? Yeah. Sorry? Sure. And I mean, again, except it's not, right? Like, because we've said you can actually break it up. But we kind of talk about it like it is, because it's the smallest particle of matter that's stable in sort of our normal lives. Does that make sense? You can break an atom apart. We call that a nuclear reaction, but that's not a stable thing, and that's not going to stick around. Does that make sense? An atom is the smallest piece of matter that will stick around and you can build something out of. So if chemistry is about building things, if it's about putting little Lego bits together, the atom is the smallest particle we have to worry about. Does that make sense? So how do we come up with that? And so I want to take you on a brief history. These fine fellows, Democritus and Aristotle, and I know which one I'd invite to my birthday party. Look at this guy. This guy looks like he's fun at a party. This guy looks very stodgy and serious. But this is Democritus. Democritus, I think that's how it's spelled. Ooh, I'm feeling embarrassed now. He's an ancient philosopher from Greece, and he is sort of what we think of the first guy to give us the idea of the atom. Now, in ancient Greece, had they done scientific experiments and discovered the atom? What do we think? No. Did you talk about this in grade 9 and grade 10 science? Did you not? That's okay. We'll talk about it now. They didn't have electron microscopes, which just now, our most bleeding edge technology now is letting us see individual atoms as like big blurry spheres, and we're like, oh my god, we can see an individual atom. But they definitely couldn't do that. And they didn't really have a scientific system the way we think of it. That's fairly modern. So how does he come up with the idea of the atom? Well, with something that we actually use in science as a starting point all the time. As a starting point, not as an ending point. He did what we call a thought experiment. And it went something like this. What if I took a piece of gold? I mean, this is a paraphrase, to be clear. I mean, he spoke Greek, so obviously this isn't his exact wording. But what if I took a piece of gold and cut it in half over and over again? It doesn't have to be gold. It could be anything, but let's say it's gold, and kept cutting it in half. Could I do this forever? In other words, could you always just keep making it smaller? I mean, obviously, eventually your knife wouldn't be, but in theory, if you could build a sharper knife, if you could build a finer blade, can you cut it in half forever and ever? And he kind of comes up with the idea that he thinks you probably can't, right? Like, if you think about a building, if you took it apart piece by piece by piece by piece, eventually a building like this that's made out of cinder blocks or made out of bricks, you're going to get to an individual brick, right? And then if you broke that up, well, now you'd be talking about something different, but even then, eventually you're going to get to like individual things. And his idea is that eventually you get to a piece that you can't cut in half. And again, this is just a thought experiment. It's just an idea. But his idea was a building block that is indivisible. Because the thing of it is, if you cut a piece of gold in half, you now have 2 pieces of gold. It's still gold. And if you cut those in half, you have 4 pieces of gold, and then 8 and 16, and it's still gold, right? But his idea is eventually you'd get to a piece that is so small but is so elemental that if you cut that in half, either you wouldn't be able to, or it wouldn't be gold anymore. Does that make sense? It'd be something else. So a building block that is indivisible, and he calls this atomos, which is the Greek word for indivisible, or the atom. Now, the problem with just a thought experiment is you get somebody who thinks something different. This is a guy you've probably heard of. We heard of Aristotle? Aristotle had his own idea. And his theory of the elements you've probably heard of. The classic 4 elements. What are the classic 4 elements? Fire, water, earth, and air. So as it happens, this is correct, at least roughly. This is incorrect. But in the absence of evidence, who's to say? You know what I mean? If you can't prove it, then who's to say that this idea is better than this idea? In the meantime, this guy looks like he had too much to drink on a Friday night frat party, and this guy looks so serious. So who did people listen to? Yeah, right, serious one. Still batting 1,000. Look at this kid. Angela, I'm such a fan. I am. I'm a big fan. I'm going to get a button. I'm going to get a button like on my shirt, and it's just going to say, Angela Fan Club, number 1. I'll invite people to join, but only if they're cool, right? We don't want no losers, right? Okay, we'll talk. Anyway, you can join the fan club, but you got to be number 2. I'm going to be number 1.
Mr. Orlando, you said no losers, so you're not number 1.
What'd you say?
You said no losers as if you're not number 1. You said you're not going to invite any losers, but you're inviting yourself.
I'm not a loser. Come on now. My mother says I'm cool. And I believe her. I believe everything my mom says. So yeah. And I mention this because it goes to show that, like, we actually had the right idea, almost 2,600 years ago. But in the absence of evidence, what good is the right idea? In the absence of evidence, it's no better than the wrong idea. As it happens, this idea takes hold for about the next roughly 2,000 years. Kind of depressing in a way, isn't it? But this idea sticks around for about give or take 2,000 years. And you still get some people who kind of buy into this stuff today. Though they shouldn't, because we have ample evidence now that it's not true. So when do we actually start getting evidence for the atom? So anyone, again, did you do in grade 9 or grade 10? Did you ever do the electrolysis of water? Was that a lab you guys did? Electrolysis is just, did you ever, like, you put a little electric current through water and you can actually get it to bubble off 2 different gases? And of course, what 2 gases would you get bubbling off if you are breaking water apart? You'd get hydrogen gas and you'd get oxygen gas. Which would you get more of? How much more? Twice as much. Does that make sense? And if you didn't do that, we'll do it tomorrow. We'll set it up. But the cool thing about it is you can see it. Like, you literally, you can do this at home today. You can put 2 thumbtacks on the bottom of a Tupperware thing and something to make sure it's sealed, put some water in there and sit that thing on a 9-volt battery, and you'll see that bubbles start to form on the 2 tacks. And for reasons we'll talk about later, the positive side of the battery is going to get oxygen forming on it, and the negative side of the battery is going to get hydrogen forming on it. You don't have to worry about why that is. But you'll see clear as day that the one of them is putting off twice as many bubbles. It's going twice as fast. And the reason is it's breaking water apart, and it's breaking it into its 2 parts, and the 2 parts are hydrogen and oxygen. That experiment actually brings us back to the atom, a whole 2,000 years later, with a guy named John Dalton. I will answer your question. I just want to get this down before I forget. Okay, so put your hand down and then put it back up in just a minute. So John Dalton, in the 19th century, breaks water into hydrogen gas and oxygen gas. And what is of note is that there's always exactly, so we have oxygen and we have hydrogen. And if we look at the volume, for every one oxygen, there's always two hydrogens. In other words, if you collect it in a tube, the tube with the hydrogen is always going to have twice as much gas in it. Does that make sense? If you collect it in a balloon, the balloon with the hydrogen is always going to have twice as much. But here's the interesting thing. The mass is that for every hydrogen, the oxygen is actually about 8 times heavier. Does that make sense? Even though there's twice as much hydrogen, the oxygen weighs 8 times as much. And why is that? Well, Dalton is smart enough to use this to figure out that he determines that these must be particles. That water, no matter where you get it, if you get it from the Thames River, or the Atlantic Ocean, or a pond, or whatever, is always 2 hydrogens for every 1 oxygen. And furthermore, that if hydrogen weighs 1, oxygen weighs 16. Right? In other words, he determines that water must be made of 2 different kinds of things. And the interesting thing is, they start doing this with all kinds of substances, and they find you can break all kinds of substances apart. Does that make sense? You can take carbon dioxide, and if you do a bit of work, you can get to be carbon and oxygen. And you can take sodium chloride, and if you do a bit of work, you can get to be sodium and chlorine gas. And you can break all these things apart. But then some things you can never break apart. You can't break oxygen apart. Once it's oxygen, you can't get smaller. Does that make sense? It won't go to anything less. Once it's hydrogen, you can't get it to be anything less. And so they start studying this, and they start determining that the atom is when you get something that can't be broken down further, and it turns out you can get oxygen from a bunch of different places. Water will give you oxygen, but carbon dioxide, which is a very different thing, will also give you oxygen. And weirdly, bless you, weirdly sugar, which is a very different thing, if you break it apart, will also give you oxygen. You can get it from all these different places, which means that particle is used as a building block to make a bunch of different stuff. Does that make sense? A little bit? How am I doing? 6 out of 10? 6.5? You can be honest. 10. Oh, A+. Look at that. Final grade in the books. So then the idea here is that an atom is the smallest building block of matter. And there's different types. And they have different properties. Oh my goodness, excuse me. So we talk about atoms being the smallest building block, but really what we mean by that is that it's a collection of building blocks that can't be made smaller than they are. In normal chemistry, I can't take copper and make it smaller. I can't break it into oxygen and carbon or something like that. Now, as it turns out, outside of chemistry, we can do that. When we actually start taking atoms individually apart, that is doable, but it's not chemistry anymore. What kind of reaction is that? We typically classify this under physics. Nuclear reactions. Yeah, fission, fusion, that's what's happening in the sun all day, every day. Hydrogen atoms are bumping into each other and turning into helium atoms. But that takes a tremendous amount of energy to make happen. And it releases a tremendous amount of energy. It's happening in the sun all the time, but we also use it when we make nuclear reactors. We can get atoms to undergo that, and they produce tremendous amounts of energy. Unfortunately, in human history, we also used it to make weapons, because this is what people do. Give a kid a stick, he's going to hit somebody with it, right? You give ability to smash atoms together and release tremendous amounts of energy, and they're going to turn it into something you can drop out of a plane and kill millions of people, which is problematic, but it, as it turns out, seems to be a bit of our nature. So I want you to see if you can remind me what the three particles are. Relatively speaking, what their mass size is, what its charge is, and where in the atom you find it. I'm going to give you 2 minutes to see if you can fill that out. And we'll obviously take it up, but see if you can explore the depths of your memory and see what you recall. Yeah, 2 minutes. So. Yeah. Okay, the three particles. We have protons, and then we have electrons, and then we have neutrons. Okay. Relatively speaking, what are the heavy ones? What are the heavy ones of these? Yeah. Protons and neutrons both have a mass of what we call 1U, or 1 atomic mass unit. Those are the same things. More often now you'll just see the U. And what about the electron? Tiny. Functionally it's 0, but it's approximately that. About 1/10,000th the mass of a proton. So much, much, much slighter. Sorry? It's a mu, which is basically a letter U. It's Greek. Yeah. What about size? These are, relatively speaking, large, and the electrons are tiny. Now, again, when we say relatively, atoms are incredibly tiny. But within the atom, the protons and the neutrons are the big heavy parts, and the electrons are tiny. Does that make sense? Which relates to where we find them. Where do we find the protons and the neutrons? In the center, the big dense center of the atom, which we call the nucleus. Where do we find the electrons? They orbit the nucleus. Very good. Okay, we're good. You know, I sound good. All right. What about charge? Shut up. Shut up. Nobody likes you. I'm doing my best. All right. What about charge, Sam Brady? Electrons are negative. Good. Very good. Electrons have a charge of -1. Protons are positive. They have a charge of +1, which is to say a proton is exactly as positive as an electron is negative. They work in opposition to each other. And a neutron has no charge. It is neutral. It's a charge of 0. We could draw this, and I'm going to do so very schematically. But let's say we wanted to draw, I don't know, let's say beryllium. No, let's just say lithium. I'm feeling lazy. Lithium, if you check the periodic table, has 3 protons, and it has 4 neutrons. These collectively make up what we call the nucleus. And then its electrons are found in orbit. And we could draw that like this. And for reasons that we will remind you of later, well, actually I should say, following rules that we will remind you of later, and for reasons that you will learn if you take grade 12 university chemistry. It turns out that the first orbit can hold 2 electrons, and then that third electron actually has to be in its own orbit. It has to go up to another one. Does anyone remember how many electrons would fit in that second orbit? 8 is good. Does anyone remember how many fit in the third? Also 8. Yeah. If you can't remember, where could you look? Periodic table. It's a big old hint machine. Which, let's talk about that. The basic information from the periodic table we can find here. Hey, we're going to finish this even with my introduction. Look at me. I am so focused. I'm so on point. Right? Slay, queen. How'd I do? That was youthful, right? Was that good? Did I do well? That was good. Finger on the pulse of youth culture team. It's hard being so in touch with how the youth think and all. But I'm hip to it, if you know what I'm saying. You cool cats, you. All right, let's get to it. So, shut up. So we call this number here what? The atomic number. And this is the most important thing to know about any atom, because this is the definition of an atom. This is the number of protons in the nucleus. And that is what defines an atom. In other words, any atom that has 11 protons in its nucleus is sodium. Everything else can change. You will find that neutrons can actually be taken away. They can be added, but it's still sodium. Electrons can be taken away or added. That will have an effect, but it will still be sodium. Our definition of an atom is based on how many protons it has. If you had a proton, one more proton to sodium, what would it become? It wouldn't be sodium anymore. It would be magnesium. If we took a proton away from sodium, what would it become? Yeah, very good. Does that make sense? So the definition of an atom is its atomic number. That determines what the atom is. So this defines the species of the atom. Then on the periodic table, it is helpful not just to give us numbers, because hard to remember that, right? If we always just called them by number, if we're like, yeah, number 12. Imagine if we just always called you by number. I always had this image in my head that one year I would memorize every student's student number, and instead of calling them by name, I would literally just call them by number. Be like 468235514. Any answer to this? I thought that would be whimsical and funny. But then I remembered that I struggle to remember students' names as it is, so I would be unlikely to successfully memorize all of your student numbers. In university, I knew all my friends' student numbers because they used to post grades on the wall because there was no like online portal or anything. So they had a much lower tech thing of they would just print all the grades out on paper and just stick them on the wall. And of course, it's like 500 kids in a class, so they're in order of student number. So I always knew. I'm like, my buddy Greg, he was 2683811, so I could look and see like if he did better than I did. My buddy Chris was 2683947, and I could check him. You know, like you could go look and see how people were doing relative to you. I always beat Chris. I never beat Greg. I was right in the middle child in our academic relationship. Anyone here a middle child? Any middle children? The reputation is the middle child gets ignored. Do you feel that? Is that accurate? Does that fit? Interesting. Would you say that's like the exception though that like suggests the rule? Because I think for most people the reputation is middle child. Like I'm the baby, and my understanding is the baby gets spoiled. But I wasn't spoiled. My parents just loved me better than all the other ones because I was perfect and wonderful. But I'm not spoiled. Right? And then like the oldest child like gets ignored for affection, but gets all the criticism. Any oldest children in here? Does that feel right? That the criticism all comes your way. Yeah, this is my understanding of parenting. Okay, every element has a 2-letter identity that we give it, and we call this the symbol, which is kind of weird because we tend to think of symbol as being like a drawing, not 2 letters, but we call it the symbol. So each element has a 1 or 2-letter symbol. By the way, how stupid is that? Like, why not just All of them 2 letters. That would work, right? Why can't it just be 1 letter? Because there's too many elements, right? Like we only have 26 letters, and there's, about 114 things on the periodic table, so that doesn't work. But 2 letters would get you there, right? But the way it is, it's 1 or 2 letters. And keep in mind, it's either uppercase or it's uppercase, lowercase. Does that make sense? Well, those are, well, it's not that we don't like to talk about them. They're just, that UU is for unnamed at that point. So, and they've since been named. That's an older periodic table. So we're going to not count those. But even then, the first letter would be uppercase, the subsequent letters, lowercase. And then, of course, I mean, I can't even believe I'm pointing an arrow to this and writing something, but here we go. What is this? This is its, that's right, that would be its name. Do I need to put a definition of that? This is the word we use to refer to this element. Which I will actually say, having made that joke now and then in the moment, having to come up with a definition, defining the word name, not as immediately obvious as you might think. I had a little moment of panic there. How'd I do? I'd give that a B. I think that's pretty good. That's a B. That's a level 3 answer. 3 minus, level 3 minus. I don't know what the levels mean. I'm a high school teacher, and can I ask you a question? If you asked 100 different people in our education system what a level 2 means, do you think any 2 of them would agree? If you got a level 1 on something, did you pass? Yeah, you passed. Yeah, which is ridiculous, right? But if your teacher puts a level 1 into the grade book, what do they almost certainly put it in as? 1 out of 4, which is that a pass? No. Do you see what I'm saying? The level system sucks. It's so stupid. And it didn't exist when I was a kid. When I was a kid, we had letters. And then I bet you somebody getting paid like $600,000 a year was like, letters. That's so 1972. What if numbers? 1, 2, 3, 4. Yeah, that'd do it.
They could have made like 10.
Right? This one's 4 is not enough resolution. And so then people start doing, well, that's a 4 plus, and that's a 4 minus, and that's a 3 plus, and what does that even mean? And do you want just so you know in advance, I mark every single question you will write, I mark out of 10. That to me is obvious. How's that answer? 6 out of 10. Orlando's class, how's it so far? 2 out of 10. Orlando's hair, how's it? 3.5 out of 10. Orlando's finger on the pulse of youth culture, 10 out of 10. You know what I mean? Like, it just, you know it. Everyone knows what that means. Hair, bad. Class, worse. Finger on the pulse, can't deny it. Undeniable. Toughness, 10 out of 10. First thing I noticed. Anyway, what's this last one here? This is what we call the mass number. Now, previously, we already learned what 2 things give an atom functionally its mass. Obviously, all 3 contribute, but which 2 meaningfully contribute? This is basically, i.e., if we round it, the number of protons plus the number of neutrons. Very good. Which means if mass number equals protons plus neutrons, what if I wanted to know how many neutrons? Anyone want to do a little bit of algebra here? Go. Wait! Your answer is wait! You put your hand up to volunteer, and the answer you volunteer me is wait? No, that's fine, I'm waiting.
So you take like 22.9.
Yep.
And then you subtract 11.
Oh, you're good. Very good. And obviously, what should I do with that? Yeah, so we would say the rounded mass number, right? Minus the atomic number. Very good. So that, if we want to know how many neutrons are in an atom, we can do that. Let's do that for sodium. Do that right here. E.g., sodium. Let's take a look at sodium. How many protons? 11. How many electrons? It's got to be 11. Why does it have to be 11? This is true for all matter, generally speaking. As a rule of thumb, if you touch something, it does not electrically shock you because it doesn't have a charge. Most things are electrically neutral. And if they're electrically neutral, that means they have to be exactly as positive as they are negative, which means if they have 11 protons, because they have to, because that's the definition of being a sodium, then they have to have how many electrons? 11. Now, you can change that. That device over the, anyone ever used it before? Static generator? You can accomplish the same thing by going home and rubbing your sock feet on the carpet, right? And then if you touch somebody, you can shock them because you can actually use your socks on the carpet to steal some of its electrons. And then you can run up to your sister and go near her cheek and go like, ha, and give them to her. And it shocks her. Does that make sense? But generally, the number of protons is the same as the number of electrons. Does that make sense? We'll just make a quick note of that. Same as the number of protons in a neutral atom. And then, for sodium, its neutrons would just be, what is 22.989 rounded? 23, minus the atomic number, which is 11, which means there's how many neutrons? 12. Does that make sense? Presumably you did that in grade 9, I'd imagine. And then did you do it again in grade 10? Awesome. So that hopefully feels comfortable for you. If it doesn't, that's okay. Again, I can't stress enough. We're teaching this right from day one. So if there's any content we come up to that gives you trouble, tell me that. We can slow down. If you're having trouble with it, likely 10 people are having trouble with it, so that's good to know. We're going to go at a pace in this course where everyone learns what we need to learn, and we all succeed together. We're a team. We succeed together, we fail together. I've always thought it'd be, in my platonic ideal, I'd give the whole class a grade. And everyone would get it together. And it'd be communal. And those of us who do well would have to help those of us who struggle so that we'd all do well. Anyway, I'm not allowed to do that because that's inappropriate, but that's what I would do. There's some homework on here. Guess what I want you to do? Yeah. All right? So it's not much, but listen, look at me. Look at me. This isn't the course to be in if you don't like doing homework. It's just not, okay? I'm not going to give you a ton. I don't give homework for the sake of it. I don't give busy work. I'm not trying to waste your time. Just look at me. There might be the odd brilliant person out there who just this stuff comes real quick and they don't need to practice. Most of you will need to practice. If you're wondering, is he talking about me as the brilliant one who doesn't need to practice? I'm not. All right, I promise. I'm not. All right? Practice. Do your homework. All right? It won't take you long. And let me tell you something. Look at me. You will save time. Because you do your homework every night. This might take you 10 minutes tonight. Might. Maybe 15. Right? If you like sip a tea while you're doing it. But boy, that's a lot easier than 2 days before the test, starting to cram and study and freak out. You know what I mean? Just do your homework. Every day. Do your homework every day.
Is that the secret?
That's the secret.
I stole page 1 of your handout, which the rest are in copier, I guess.
They're up
yeah,
or in the front?
this one missed the staple. They're in copier 1.
Okay, perfect.
I think you also have stuff too, which is not printing this one. Now
Yeah, I canceled all my jobs up there, so I hope they didn't all print up there. But if they did, no, whatever. Yeah, copier 1 just, it was, 2 was just saying waiting to print.
Copier 1 was like, on order paper in tray 4. I'm like, did you try tray 3?
I know, it's so upsetting. All right. Oh, hey. Oh, one more thing. As a rule, we're going to be doing lots of pop back into the lab and things like that. Really try to avoid, if you possibly can, binders, books, and backpacks and bags and stuff in here to the best of your ability. If you can use your back or your locker, that really is ideal.